Buenos días y gracias por asistir a este acto de defensa de la tesis doctoral titulada Economía circular en el sector del galvanizado en caliente, demostración en planta piloto y análisis de sostenibilidad ambiental, para optar al título de doctora por la Universidad de Cantabria. Esta tesis ha sido supervisada por la catedrática Andrea y por la doctora María Margallo. A continuación, voy a iniciar la presentación sobre el marco de realización de la tesis en lengua castellana. Después, utilizaré el idioma inglés en la presentación de la motivación, los objetivos y resultados, para finalmente retomar el castellano en las conclusiones. Esta tesis se ha desarrollado en la Universidad de Cantabria, en el Grupo de Investigación de Tecnologías Ambientales y Bioprocesos, del Departamento de Ingenierías Química y Biomolecular, dentro del programa de doctorado en Ingeniería Química de la Energía y Bioprocesos. La investigación realizada ha sido financiada por el proyecto europeo Life to Active. La tesis opta a la mención internacional, cumpliendo los requisitos de realización de una estancia de 3 meses en el Departamento de Ciencias e Ingeniería do Ambiente de la Universidad Nova de Lisboa, bajo la supervisión de la doctora Grasa Martínez. Además, el documento de tesis ha sido evaluado favorablemente por 2 evaluadores externos, y un miembro del tribunal pertenece a una institución extranjera de prestigio internacional. En cuanto a la difusión de los resultados, esta tesis ha dado lugar hasta el momento a 4 artículos publicados en revistas internacionales y un 5º artículo enviado en proceso de revisión. Además, se han presentado 10 contribuciones a congresos nacionales e internacionales, habiendo recibido el premio al mejor póster otorgado en la escuela de verano organizada por la European Memorial Society. En esta presentación comenzaré por la contextualización del trabajo, seguido del escalado de la tecnología de extracción con solventes no dispersivos para la purificación de ácidos de decapado agotados, continuando con los estudios de sostenibilidad realizados para finalmente presentar las principales conclusiones. I will introduce the background including the circular economy in the context of waste management, the role of zinc in the industry and the generation of spent clean acids, and finally, the aims of this work. The stock for raw materials is far from unlimited, as the linear economy assumes, and the demand is increasing, resulting in resources depletion and environmental degradation. In the search for solutions, strategies for promoting sustainable cycles are rapidly gaining interest, such as the circular economy, because they are expected to minimize waste generation and to reduce the demand for virgin materials. However, current waste management strategies lose a large part of resources in both Europe and Spain. Europe adopted the new Circular Action Plan in the last 2020 as one of the main elements of the European Green Deal. In Spain, the strategy España Circular 2030 gathers the national measures to achieve a sustainable, decarbonized, resource-efficient and competitive economy. In the context of the process industry, circularity brings benefits of substantial material savings and reduction of environmental impacts. Regarding circularity, metals that traditionally come from primary sources are being replaced by secondary sources to fulfill their demand. Iron, aluminium, copper, zinc, lead, and nickel account for more than 98% by mass of all metal and metal alloy products used in the world, whose predicted demand is going to increase except for lead. This situation poses the serious challenge of how the demand for metallic goods and services by a growing world population can be met without exceeding the carrying capacity of the earth. Zinc is the 6th most produced metallic element worldwide and has been identified as one of the most easily recyclable materials, whose end-of-life recycling rate is around 40% at worldwide level. The recovery of zinc from waste is a strategy that has been applied for many years. However, in this context of resources depletion and increasing demand, new sources of zinc must be analyzed and promoted according to the circular economy. This figure shows the production and research of zinc in the recent period. Globally, around 13 million tons are produced per year, with China, Australia and Peru being the top zinc producers. In support of the economic interest for zinc recovery, this figure shows the evolution of zinc price in the last 5 years. The price of zinc, like that of metals in general, is fluctuating. Specifically, zinc costs have varied, reaching a maximum of $4,500. Nearly 60% of zinc is used in galvanizing to protect the steel from corrosion, being the construction and transport sector the main demanders. Thus, zinc demand is mainly affected by the zinc intensity of galvanizing as well as by the demand of galvanized steel products. As confirmed by the next figure, the production of zinc in green and steel in blue can be correlated. There are two main ways of zinc coating: hot dip galvanizing and electrochemical galvanizing. In the hot dip galvanizing process, steel pieces are immersed in a molten thin bath to avoid steel corrosion. In this process, residues with high content of zinc are generated. Solid residues such as ash and hard-rust zinc are generated in the drying and molten thin bath stages, with a high zinc content that is recovered by means of mainly metallurgical processes. Spent pickling acids are generated in the pickling stage, whose objective is to clean the steel surface before the molten thin bath. Nevertheless, for the SPA, there is not an established route for zinc recovery. This thesis is focused on spent pickling acid, that typically consists of free hydrochloric acid, iron, zinc, and chloride ions. SPA may contain low concentration of other metals, such as manganese, in addition to surfactants, inhibitors, and stabilizers. More than 300,000 cubic meters of SPA are generated per year, only in Europe, their toxicity being one of the major concerns. Besides, SPA is classified as a hazardous waste according to the European Waste List, and therefore it requires a suitable treatment before disposal. The reference treatment of spent pickling acid consists of neutralization precipitation followed by solidification, stabilization, and disposal in non-hazardous landfills. Although neutralization is the most economic method, some disadvantages are the excessive sludge formation and, in the long term, the possibility of leaching of heavy metals to groundwater. So, the handling of SPA constitutes one of the environmental challenges of the galvanizing industry. This reference SPA treatment is being replaced by innovative alternatives that have the objectives of acid recovery and metal recovery. Based on previous work of the research groups of the department and the literature, membrane-based solvent extraction appears as an effective solution for SPA management with focus on metal recovery. But why membrane-based solvent extraction? This technology enables the selective transfer of species between two fluids, forming an interface, where the desired species are selectively extracted from the feed phase to the extractant. In addition, membrane contactors allow for process intensification. The non-dispersive solvent extraction technology is a configuration of membrane-based solvent extraction that facilitates the scale-up from laboratory to pilot plant because it avoids a subsequent separation step, as one module is used for the extraction between the feed and the extractant, and in a second module, the loaded organic phase is brought into contact with a stripping phase, in which the desired species is finally recovered. The group's background and the literature review led to the selection of tributyl phosphate as extractant and water as a stripping agent. Tributyl phosphate has some advantages such as the high zinc extraction, high selectivity of zinc over iron, and high loading capacity. Similarly, the volumes of the three phases were selected to maintain the volume ratios previously optimized in the lab scale studies. An integrated view of a metal recovery process from a waste system usually entails the combination of a separation purification stage followed by a recovery stage. In this diagram, the separation of zinc and iron of the SPA is performed in a non-dispersive solvent extraction unit. The purified zinc solution is derived to the electrowinning step for metal recovery. This approach has already been studied in the lab scale as independent consecutive steps. This thesis has been developed in the framework of the European project Life to Acid, with participation of several partners, which has allowed the integration of non-dispersive solvent extraction and electrowinning technologies at pilot plant scale. This slide shows the pilot plant that has been designed, built, and operated in this project, in which three main parts can be viewed: the non-dispersive solvent extraction unit, the electrowinning unit, and the scrubber for chlorine absorption. The integration of non-dispersive and electrowinning technologies allow the recovery of three products: secondary zinc, iron chloride, and sodium hypochlorite. This doctoral thesis has gone beyond the objectives set by the Life to Acid project, establishing the route for the application of the circular economy in the hot dip galvanizing sector. The first objective was the scale-up of non-dispersive solvent extraction technology, increasing the technology readiness level from 4 to 7. This thesis has focused on the technology demonstration of the non-dispersive solvent extraction process, In the case of electrowinning, the experimental demonstration was carried out by other partners of the project. Regarding the evaluation of the recovery products, this thesis has focused on evaluating the reuse of iron chloride. The second objective was to analyze the environmental sustainability of the life-to-acid technology that integrates non-dispersive solvent extraction and electrowinning. The life cycle assessment tool was used to identify the main impacts of the hot dip galvanizing process. Next, the alternatives of SPA treatment were compared, taking into account the material credits of all the recovered products that were zinc, iron chloride, and sodium hypochlorite. And finally, the integration of the life-to-acid technology in the galvanizing process was evaluated.